Okay guys, we are at a kind of exciting project within the year where you get to make this toy automata, and the different motion up and down or a little bit sideways within that automata toy is created by these things called cams. We've got a pear cam on the screen as our diagram. It's called a pear cam because it looks like a pear. As you design a cam and figure out what size it needs to be and what shape it needs to be, there's a couple bits of terminology that I want you to understand, and they're shown on this diagram. The first one is greatest radial dimension. This is probably the most important one because it's going to affect the size within the box that we're creating. You see that the greatest radial dimension goes from the center hole. It's not really the center of the cam necessarily, but it's wherever the axle is going through, and it goes to the furthest distance along the outside of the cam. The least radial dimension also goes from the axle hole, but it goes to the closest spot on that cam. So I've got a pear cam here and axle going through it, and you can see that this would be the greatest radial dimension from that axle to the furthest point. This would be the least radial dimension from the axle down to the closest point. Now, keep in mind this axle rotates as well, and so this is still the greatest radial dimension, but now it's on the bottom. If I would rotate it all the way around, it would now be back on the top. Okay, you can see that within an automata as well. Here I've got the greatest radial dimension beneath the axle, but if I rotate it around, now it's at the top. And when it's at the top, that's where that yellow piece, it's called the roller inside, pushes everything, the follower and whatever you've got up top here, it pushes it up. So when the greatest radial dimension is above the axle, all of your stuff up here is going to be at the highest level. And when that greatest, or when the minimum radial dimension is above the axle, now everything's as low above the top of the box as it will get. Okay, so those are two terminology that you should know. And that's going to help us determine exactly how large this cam should be. Okay, one thing that you should know about the box itself is that the distance from the very top of the box here to the bottom of the box, this opening where you have room to build stuff, is exactly 4 inches. Okay, so we're going to total up a bunch of items. We're going to add them up, the things that are inside that box, and we know that they need to be 4 inches. The things that we're going to total up really are, we're going to leave a little bit of clearance at the bottom and the top to make sure nothing's rubbing. We're going to talk about the cam itself, how large that has to be, and then don't forget about this little yellow piece called the roller that sits on top of the cam. Okay, so we're going to start with the maximum radial dimension, but we're going to add it twice. And the reason we're going to add it twice, remember, is that this maximum radial dimension could be on top of the axle, but even when I turn this thing, it could also be below the axle. So we're going to have to account for it here and here so that it doesn't hit the top or the bottom of the box. Like I said, we're going to add a top clearance. My suggestion is about 1/4 of an inch, and a bottom clearance about 1/4 of an inch. And then the last thing that's inside that box is the roller, which should be about 0.3125 inches. Okay, so all of this stuff together has to add up to 4 inches. So if I take away from that 4 inches, if I take away the roller and I take away the bottom and the top clearance, that leaves me with about 3.1875 inches. Okay, so altogether, 2 of the max radial dimensions should be 3.1875 inches, and if I split that, it's about 1.593 inches. Okay, so I just average, or not average, but a rough estimate of that would be about 1.5 inches is where you want to be for the maximum radial dimension. That's going to be real important as we go on to this next bit of information. In your packet, you have something as an example that looks kind of like this. It's a motion graph. This is what you're going to originally start with to create the shape of your cams. And you'll notice it's got the distance on the side, and it's got the angle of cam rotation. So as you turn the crank and the cam is turning, it's showing it being turned at a 45 degrees, now 90 degrees, until you get all the way around to 360 degrees. Okay, the reason I'm showing you this is because we have to be careful with that maximum radial dimension. This distance from 0 to the lowest point up to that 1.25, that would be your minimum radial dimension. Okay? The maximum radial dimension is to wherever you got this thing at the very highest point. So now the difference between those two, from the 1.25 up to the 2.375 that I've shown in green here, that's your maximum displacement, how much movement you're getting on this entire toy automata. Okay, so we're really more concerned with this portion of the graph that shows how much movement and what kind of movement is happening here. It looks like for this automata, the items are going up, up, up. They go up a little bit more steeply. They come down kind of steeply, and then gradually come back to their resting spot, and they start that over again. Okay, so maybe that is something like a wave in the ocean. Okay, that would be an example. This graph, you're going to create something kind of like it, but you've got to be careful. This graph is actually a bit higher up than it should be for your purposes. Remember, we said 1.5 is about the maximum radial dimension. This is going over that maximum radial dimension. Their maximum radial dimension is 2.375. If you had that cam inside this box, it wouldn't fit. It would be hitting the top or bottom of the box. Okay, so here's an example of what you're going to do in your designing a cam packet. And I've got this red line right in the middle at 1.5 as a reminder, your graph should not be going over the top of that, or your cam's going to be too large. You do probably want it going up to that point because you don't want to have something really low and then you barely get any movement, like it's just bouncing a little bit. But be careful not to go over that 1.5. Okay, we're going to get rid of that now. Let's say we wanted to create something kind of like a jack-in-the-box that rises kind of slowly, and then at the end it just goes right back down, and then rises slowly and goes back down. Okay, remember, we're not going to go over that 1.5, but that's going to be the high point of that jack-in-the-box before it drops back down. Let's start at, I think, a 1/4 of an inch would be a good minimal radial dimension for us. If that's at 0 degrees, in other words, the starting point of the cam, then we should have that same thing at 360 degrees, because after we turned it a full rotation, it's going to be in that same spot. So just before we get to the end of that, I'm going to put the maximum radial dimension. Okay, so I'm going to have this motion go up, 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 up until we get to that maximum radial dimension, and then I'm going to have it drop back down. The rest of the stuff in between here, it's not super important exactly where you put it. It's going to be kind of a curve anyway, so it should be somewhat smooth. I'm just going to have them go up about 1/8 of an inch to begin with, and then here we'll jump up a little bit, 1/4 of an inch at a time till we get to that, and then it's going to drop right back down. And then this would have to be, if I go on to the next one, this 45 degrees is going to be the same as this 45 degrees. That motion starts all over again. Okay, so this would be an example of the motion itself of a jack-in-the-box that's slowly going up and then comes right back down and then starts over again. That's the first step in determining the shape of your cam. Right now, this doesn't look like a shape itself, it just looks like the motion. But we're going to take these exact points of data and transfer them from this linear graph to a polar coordinate grid, which is a round graph, and you have that in your packet as well. So the first point that we're going to put on that grid is at a 0 degree angle of rotation, but it's at 1/4 of an inch. The second one, then, we're going to look at 45 degrees and put it at 0.375 of an inch, and so on. So all these same points that you see here, I'm going to put on this next slide. Okay, here's the polar coordinate grid. We said at 0 degrees, and the degree markings are along the outside. And you'll also notice that we are going counterclockwise as we do this. Here's 0 degrees on this first vertical axis. And this 1 in here is 1 inch. It's this first darker blue circle, and here's 2 inches. Remember, we're not going to go past 1.5 inches because that needs to be our maximum radial dimension for the box that we're given. And so if I go on the 0 degree, 1/4 of an inch starts right there. That's my very first point. If I now turn 45 degrees counterclockwise, so somewhere along this line right in here, we went up a little bit, 1/8 of an inch, so it's going to be there. You notice we're getting closer and closer to that 1 inch ring. At 90 degrees, we went up another eighth of an inch. At 135 degrees, we went up another eighth of an inch. At 180 degrees, we went up another eighth of an inch. We jumped a little bit higher when we got to 225, and that's when we finally hit the 1 inch radial dimension. Jumped up another quarter of an inch there, and then finally we jumped up to 1.5 inches when we got to that 315 degrees, and then when we were back at 0, we were back here at our initial start, our minimal radial distance of a quarter of an inch. And so without recognizing anything else, you might say, well, okay, fine, it's the same data, it's just plotted differently. But here's why this is so important. Because now with this shape, we can connect these dots from the first point of data to the second one. And if you were doing this on Autodesk Inventor, you're going to want to make this a smooth curve, not straight lines, and I can only do so well here on this computer program. Okay, but you're going to get the shape that looks like this. This is the actual shape of the cam that would produce that jack-in-the-box motion, and it's the exact size of the cam that would produce that jack-in-the-box motion. So we're going from that linear graph that shows the motion we want to see, and now we're putting it on this polar coordinate grid, and we're able to come up with the exact cam, exact distance. Okay, so that's how you are going to work through the process for each of the 3 or 4, however many cams that you've got. You're starting off with the motion you want in the first place, and then you transfer that data so that you can find the exact shape and size of it. Blessings on your work.